Welcome back to the final lesson of the Machine Learning 101 course. Today we will explore concepts beyond supervised learning, including unsupervised learning and generative models. So far, we have covered supervised learning algorithms. In all these examples, the training data was accompanied by true labels, and we expected the model to learn how to predict those labels accurately for unseen data. We started with some of the simpler algorithms like linear regression, logistic regression, and decision trees. Eventually, we learned about neural networks and how deep learning has proven to be a game changer, especially for problems involving unstructured data like text or images. Now, let's understand more about unsupervised learning.
Video, we learned about supervised learning, where the machine learning model learns by making use of labeled data. Now, in unsupervised learning, we have unlabeled data, meaning we have data, but we don't know the corresponding class or target for the features. This process is oftentimes more complex, but it has the huge advantage that it does not require upfront human intervention to label the data. But if the data isn't labeled, then how is the model learning? Essentially, the model is trying to figure out some kind of structure in the data and will extract the useful information from it. A popular example is object recognition, a common task in computer vision. Here, the model finds similar looking objects and marks them without knowing its specific label. Each group has its own characteristics that the model learns to identify, and afterwards, we can very easily define the associated label for this group.
K-means clustering is one of the most popular algorithms used for clustering. This is not to be confused with k-nearest neighbors, which is under supervised learning. Both leverage the concept of nearest neighbors, but are still very different algorithms.
It splits the data into distinct groups based on the features that are supplied to it. There are a number of clustering methods available, such as dbScan, Gaussian mixture modeling, and also k-means clustering, which is going to be the focus of this video. The main objective of the k-means clustering algorithm is to reduce or minimize the sum of the distances between the center of the cluster and the other data points. So let's have a closer look at how k-means clustering actually works. To illustrate the process of k-means clustering, we can use this simple data set plotted on a scatter plot. The first step in the process is to define the number of clusters that we're going to want to generate. There are a number of ways that we can identify the optimum number of clusters, and we will see an example of one of these methods in the Python tutorial section. So to keep things simple for illustration, we're going to work with 3 clusters, which means that the k in k-means is equal to 3. So after defining the number of clusters that we want, our next step is to select k random points within our dataset. In this case, we are going to be selecting 3 random points. These selected points will form the starting point for our clusters. We can then calculate the Euclidean distance between the cluster center point and all other points. If we take this point here, for example, we can see that it is closer to the red cluster compared to the green and yellow clusters. As a result, it gets assigned to the red cluster. We then repeat this process with all other points on the scatter plot until they have been assigned to an appropriate cluster. After all the points have been assigned to a cluster, we can then calculate the mean point of each cluster, which are represented here by the x's. After the new mean points have been calculated, we can then repeat steps 3 to 5 and check if the points belong to the same cluster or to a different one. As we see here, a few points have changed their color, as they are now closer to different mean points. Once the points have been reassigned, we can then recalculate the mean point and repeat. Eventually, we will reach a point where the mean points of the clusters do not change, and then we have our final clusters. And this is just a very simple illustration of how k-means clustering works.
In today's world, we come across recommender systems everywhere, from YouTube to Instagram to Netflix and Amazon. We depend heavily on what these apps recommend to us. Let's learn how we can approach a movie recommendation problem using unsupervised learning.
Given observations of a user's past behavior, predict which other things that same user will like. For example, based on Alice's viewing history, will she like The Matrix or Grapes of Wrath? We can represent user preferences graphically as connections between people on one side and things on the other, such as movies. Here, the strength of connection is visually represented by the thickness of the lines. So the problem is to fill out all of these missing connections we don't yet know, shown in red. But because of the messy, unpredictable nature of people's taste, we can never perfectly predict what they will like. Because, for one, it involves a guess about the future based on something you've never seen. And two, the answer is always in flux because people's tastes change over time. What we can do is try to estimate those values as best we can, using whatever data we have access to. So, regardless of the context, we can describe the problem in the following mathematical form. We use a matrix, which is a collection of numbers organized into rows and columns, where the rows are users and the columns are items, in this case, movies. And each cell in this matrix contains a number that describes how much each individual likes each movie. For example, we could use a scale from 0 to 4, where 0 would represent I hate it, 2 is neutral, and 4 is I love it. At any given moment, there will be some set of preference data for users and movies, but it will be incomplete because users have only seen and rated a few movies each. And so the problem boils down to trying to predict these missing values. How should we make these predictions? There are two general approaches to this problem. The first is called content filtering, which is to use information we know about people and things as connective tissue for recommendations. It's like asking Alice questions about what kinds of movies she likes to figure out if she will like The Matrix. It begins by labeling each person and movies with some known attributes, or what we call features, for example, action and comedy. That means if Alice likes comedy and hates action, we can represent her as 3-0. Each movie is also mapped to each feature in the same way. For example, The Matrix has no comedy and lots of action, so we could represent it as 0-4. And to determine whether someone will like a movie, we need to multiply these factors together. So we could represent the strength of connection between Alice and The Matrix as 3 times 0 plus 0 times 4 equals 0. So our estimation is that she will hate the movie. So to make our predictions, we first need to gather this feature data for every user and movie. To simplify, let's return to a matrix representation. We can store this information in two matrices. One defines the mapping between people and features. The other defines the mapping between movies and features. And by multiplying these two matrices together, using matrix multiplication, we get an estimated strength of connection between every person and movie. And if we'd like, we can normalize our data to make sure the scale stays between 0 and 4 by dividing all values by 8 and rounding to the nearest 0.5. That's one way to solve this problem, known as content filtering. The problem is, it's overly simplistic and not very accurate. That's because there are obviously more relevant features of a movie than just comedy or action. The obvious way to improve this is just to include more features. If you recall when Netflix started, it did just this. It would ask new users to fill out a laundry list of questions about their preferences before presenting them with suggested movies. And this leads to the problem of having to collect all of this preference data on users. Not only is it a burden for users, it's also prone to failure, as we aren't always great at describing our own preferences. Sometimes we simply can't explain why we like things. We just do. Which brings us to the other approach, called collaborative filtering. The motivation for collaborative filtering comes from the idea that you will probably like things people with similar viewing habits also like. This idea was popularized in this 2009 paper by Cohen, Bell, and Volinsky. So to begin, we can throw away the idea of dreaming up features used to connect people in movies. Instead, we flip things around and use the user preference data we do have to generate the features. For example, we might have this incomplete set of preference data, and we will instead learn or discover the relevant features based on patterns in this data. And this is done by simply reversing the problem. We first perform an approximate factorization into two matrices. And we can do this using a machine learning approach. The job of the machine learning algorithm is to guess values for those matrices, which will match the existing data in the preference matrix as closely as possible. The simplest approach is to simply guess numbers over and over until you arrive at a set of numbers which predict the data with the lowest error overall. Once this estimation is finished, we can multiply the matrices as before to fill in all of the missing values. And it's important to note that we won't know exactly what to label these discovered features, so we call them latent features because they arise out of the underlying patterns in the data. You can think of them as an average or weighted sum of the patterns in the data. They are not based on a human-defined feature, such as comedy. And that's the key insight behind this method. With content filtering, the features come from the human mind, whereas with collaborative filtering, the features are extracted directly from the patterns.
To recap, we start with a movie rating matrix that captures the user's ratings for some of the movies. This is a very sparse matrix as a big percentage of the cells will be unknown. We use matrix factorization algorithm to split this matrix into two separate matrices such that when we multiply these two matrices, we get a matrix that is very close to the original user rating matrix for the known user ratings. This is called matrix factorization. Now, we can use these user embedding and movie embedding matrices to fill in the blanks in the original user rating matrix. This way, we can predict whether a user will like a movie or not based on how well the movie's flavor matches the user's taste. In the last few years, generative AI has become very popular and sparked concerns about deepfakes. In this video, we will learn how we can train a model to be creative.
GANs are a class of machine learning techniques that consist of two networks playing an adversarial game against each other. So one of these networks is called the generator, and we can view the generator as a sort of counterfeeder. Then the other network is the discriminator, and you can view this network as a sort of detective. To give an example of the game that they can play, let's say that the generator wants to print fake money, and the discriminator wants to be able to distinguish between fake and real money. And so in the training process of GANs, the generator is trying to print let's say $100 bill, but all he comes up with in the beginning is something that looks like at the bottom left of the slide, just some random noise, because it's very bad initially. And so the detective is going to look at these two comparisons of a real $100 bill, and then it's going to look at the random noise. And so in this case, it's going to say that the one coming from the generator is fake. And so the generator was not able to fool the discriminator in this case, or the detective. But as training goes on, the generator becomes better and better, and now he might produce something that looks like this, where we have close to a real $100 bill, but as we can see, there are some Chinese signs on it and other incorrect things. So the discriminator, might look at those two and say again that the top one is fake, the one coming from the generator. So again, the generator was not able to fool the discriminator. As training goes on even further, the generator might output something that looks like this. So the discriminator might go something like this. And then output that the bottom one is fake, which is actually the real $100 bill. So in this case, the generator was actually able to fool the discriminator. So a question then is, why does this work? In the end, the generator will be able to generate dollar bills that are indistinguishable from real ones, and the discriminator is forced to guess, with a probability of 0.5, which of those is real and which is fake.
For this week, there are no hands-on exercises. However, I would strongly recommend you learn more about concepts like hierarchical clustering, dimensionality reduction, and reinforcement learning from these videos.